Every single day, the team at Royal Research processes petabytes of raw data through highly complex, interconnected analytical pipelines. To manage this incredible scale, we rely on Apache Hadoop. The framework functions by taking massive analytical workloads and distributing the processing tasks across hundreds or thousands of independent nodes working in parallel. But this distributed design introduces a specific vulnerability. The same mechanism that enables massive parallel processing also creates a sprawling attack surface, as data is no longer stored in a single location. A traditional perimeter firewall designed to protect a centralized vault is insufficient for a system where storage and processing are fractured across a vast network. Securing a distributed environment requires a multi-layered defense architecture that establishes security at the node level. This approach utilizes the concept of defense in depth, specifically adapted to wrap around the Hadoop ecosystem. We built this using 3 structural pillars: authentication to verify identities, encryption to shield the data, and authorization to govern access. This diagram illustrates an unsecured Hadoop cluster. Without security barriers, every individual storage drive and network pathway is exposed to the open network. Our objective is to systematically layer security protocols onto this cluster to mitigate specific network threats. The guiding principle for this build is that in a distributed network, trust is never assumed. It must be cryptographically proven. The first requirement of our architecture is verifying the identity of any entity, human or service, attempting to interact with the cluster. Hadoop handles this using the Kerberos protocol, which serves as the foundational gatekeeper for network authentication. The Kerberos lifecycle begins when a user attempts to access the cluster by pinging a dedicated authentication server. Once the server verifies the user's initial credentials, it generates a ticket granting ticket, or TGT, and sends this secure payload back to the user. The user terminal then passes the TGT to a centralized ticket granting service to request access to specific Hadoop nodes. The service validates the TGT and issues a final service ticket, which acts as a temporary, highly specific pass. Finally, the user presents this service ticket directly to the target Hadoop node, which confirms the ticket's validity and allows the data query to proceed. This 3-step sequence prevents node spoofing. Because the authentication keys are handled by dedicated servers rather than the data nodes themselves, an attacker cannot masquerade as a trusted node. This protocol applies to both human users and automated services communicating within the cluster. This strict verification replaces the unsecured state shown earlier, where nodes were open to any incoming connection. Kerberos ensures zero-trust identity verification before any data is ever queried. Once identities are verified, we must protect the actual data payload from interception or breach. We distinguish between 2 states of data vulnerability in a Hadoop cluster: data in transit and data at rest. Data in transit refers to information moving between different nodes within the cluster. To secure these pathways, Hadoop utilizes transport layer security, or TLS, which encrypts the data as it moves to prevent network interception. Data at rest is the physical information stored inside the Hadoop distributed file system, or HDFS. We protect this by implementing HDFS encryption zones, which encrypt specific directories that contain sensitive information. A standalone key management server, or KMS, stores the cryptographic keys separately from the encrypted data. Decoupling the keys from the storage nodes ensures that even if physical drives are breached, the data remains unreadable to unauthorized parties. Proving identity is not the same as dictating what a user is allowed to do. That is the role of authorization. Hadoop Access Control Lists, or ACLs, provide the baseline for this control. ACLs provide fine-grained, file-level read, write, and execute permissions. However, manually managing these lists across thousands of files and hundreds of nodes is a significant administrative burden. Enterprise environments use Apache Ranger to provide centralized policy administration. Ranger allows administrators to define security policies once and push them uniformly across the entire ecosystem. Ranger integrates with Kerberos, mapping verified identities to the centralized rulebook. Apache Sentry is an alternative tool that provides similar centralized integration for authorization policies. This centralized governance prevents internal overreach and accidental data corruption by verified users. These tools transform a decentralized cluster into a unified system governed by a single source of truth. Securing the cluster at Royal Research requires moving from technical configuration into active operational discipline. We implement role-based access control, or RBAC, to ensure employees only hold the permissions strictly necessary for their job functions. Data masking techniques further protect sensitive information by obfuscating data while maintaining its usability for analysis. Regular security audits and centralized logging are mandatory for identifying new vulnerabilities and ensuring compliance. Continuous auditing and rigorous patch management prevent the security architecture from degrading over time. This fully secured architecture supports the Royal Research big data infrastructure. Kerberos establishes a verified identity perimeter for every user and service. TLS protocols and KMS-backed encryption zones provide physical protection for the data payload. Apache Ranger and granular ACLs provide the behavioral governance that controls internal access. A secure big data operation integrates these specific defense layers to ensure that distributed processing power is always balanced by cryptographic resilience.